Okay, so we're gonna um um first of all, for the backgammon project, at the point that I can start writing reinforcement learning algorithms, and well, I have some ideas of how a backgammon bot should like learn, optimize how to play, all of that. But I feel like reading this helps a lot. It's 300 pages. Well, not exactly 300. You're not gonna read the references and index. All prospects, I don't know. But Samuel's checkers player, the acrobat, elevator scratching, dynamic channel allocation. Um, well, we don't know how far we can go with this, but what we can do is probably do 50 pages per video, and then we're gonna have 6 days till we have finished it. And by finishing it, hopefully I have a better idea of how, not exactly, but just a better idea that I can develop um, the backgammon bot. Because the backgammon bot, if I can show you, this is not the backgammon bot. The engine is done. Um, User versus user is done. I might need to add a little bit of. Let me see what the dad's door. Never mind. So probably need to have a system of what is it called? Persisting the activity of the user, like all the user versus user programs, and also extend that to user AI, and then most certainly AI versus AI. Um, well, what I remember from like some examples is that Monte Carlo, you don't need to have any data. You basically run the algorithm as you go. Um, you run the algorithm as you go, and basically it's just like it's a search to see, based on the way you described it, how you can maximize the reward system. For a small like game like tic tac toe, you can just win the game because there is not that much dimensionality to the whole thing. But uh, but the thing is, there's not much dimensionality to the game, but it could still have other ways to learn, probably. Like, if it was a given choice to start, would it take it? The bot should, if it wants to optimize. That doesn't, well, it can probably compute that again, but when you move to a game with the bigger dimensions of computation, then you I'm not sure if I have to have it, but it's probably better to have some analysis from some computation tell you what is better to do in what situation. But also, I was like thinking having incremental changes and basically have two AI agents just make this one a little bit better. And when it's better, just give it to this one. Let this one change. And when you let this one change, if it's better than the previous one, keeps going till you, by competition, you just like reach the maximum level of game that you can. What else? Set the step up thing. Um, um, Step up. Yeah, I was actually thinking about how you can probably have that apply to other things. I don't have enough knowledge about it to be certain, but can probably apply it to other things as well, which will make it interesting. The one up algorithm, just competitive, just getting better, and then you just work with the hyperparameters. There's that. What else did I want to say? Um, what else? What else? What else? Uh, mm, I don't know. You might be able to listen to the background noise, but what can you do? You can only do this for right now. And what else? I feel like we're good for now. So yeah, uh, the backgammon thing, how much I've done. Um, how much I've done. Um, yeah, that's pretty much it. Just like the finishing the backgammon and then going to the phase of developing. Yeah, actually, just need to just pull it up here. I'm not sure. I'm not sure how much you can hear, but whatever. So AI decide. This is where the function in. I'm writing it in Rust though. Will you see this? Hopefully. Hopefully. Doesn't matter. So I was thinking of just starting with some hyperparameters, like getting ahead, hitting, trying not to hit, not get hit, try to block movements, avoid trapment. What else? Um, just five, but one thing that mm, might be a starting point is to set these as the same, or we can even start randomly, we can even start randomly, honestly. Maybe let it play. Let it play. Because let it play. Persist the data from it. Transfer the data to another agent. Player 2. Yeah. And try to beat it. Try to have it with beating. This probably will be a little bit stochastic. So like we'll see if something works, do more of it. If something doesn't work, do less of it. Just keep trying. Try to have a bit of beating the randomness with some stochastic process. Yeah, there's that. So, okay, let's just start with this. Richard S. Sutton and Andrew G. Bartow. I feel like these guys are goats that I don't know. Etchy next 90. Etchy next 90. And then Andrew G. Bartow. He's not dead, is he? Okay. Yeah, these are crazy guys probably that I don't know. Anyways, let's just start. In memory of Harry Kilopf. Andrew Bartow. Richard S. Sutton. And that's interesting. Okay. And Harry Clough. Sutton. I've probably heard this name before. And then Bartow is less known to me, but yeah, the moment I did the picture came up and the University of Alberta, I was like, I feel like he was in a Lex podcast. He was probably in the Lex podcast. No, maybe. Podcast. Oh. Early days of reinforcement learning with Rich Simon.
In the 80s, early 80s, the neural net thing was starting to happen, and I was taking a lot of psychology classes and a lot of computer science classes as a college student, and I thought, something that can play tic-tac-toe and just like learn to get better at it, that ought to be a really easy thing. So I spent almost all of my what would have been vacations during college like hacking on my home computer, trying to teach it how to play tic-tac-toe and
programming language.
basic. Oh yeah, basic. That's my first language. That's my native language.
Is that what?
All right. Enough of that. All right. Preface. We first came to focus on what is now known as reinforcement learning in late 1979. We were both at the University of Massachusetts, working on one of the earliest projects to revive the idea that networks of neuron-like adaptive elements might prove to be a promising approach to artificial adaptive intelligence. The project explored the heterostatic theory of adaptive systems, developed by A. Harry Clough. Harry's work was a rich source of ideas, and we were permitted to explore them critically and compare them with the long history of prior work in adaptive systems. Our task became one of teasing the ideas apart and understanding their relationships and relative importance. This continues today, but in 1979 we came to realize that perhaps the simplest of the ideas, which had long been taken for granted, had received surprisingly little attention from a computational perspective. This was simply the idea of learning a learning system that wants something, that adapts its behavior in order to maximize a special signal from its environment. This was the idea of a hedonistic learning system, or as we would say now, the idea of reinforcement learning. Like others, we had a sense that reinforcement learning had been thoroughly explored in the early days of cybernetics and of artificial intelligence. On closer inspection, though, we found that it had been explored only slightly, while reinforcement learning had clearly motivated some of the earliest computational studies of learning. Most of these researchers had gone to other things, such as pattern classification, supervised learning, and adaptive control, or they had abandoned the study of learning altogether. As a result, the special issues involved in learning how to get something from the environment received relatively little attention. In retrospect, focusing on this idea was the critical step that set this branch of section in motion. Little progress could be made in the computational study of reinforcement learning until it was recognized that such a fundamental idea had not been thoroughly explored. The field has come a long way since then, evolving and maturing in several directions. Reinforcement learning has gradually become one of the most active research areas in machine learning, artificial intelligence, and neural network research. The field has developed strong mathematical foundations and impressive applications. The computational study of reinforcement learning is now a large field, with hundreds of active researchers around the world in diverse disciplines such as psychology, control theory, artificial intelligence, and neuroscience. Particularly important have been the contributions establishing the development and developing the relationships to the theory of optimal control and dynamic programming. The overall problem of learning from interaction to achieve goals is still far from being solved, but our understanding of it has improved. پدر خب بذار بعد هدفون بیارم.
نه تموم شد.
نه بذار بعد هدفون بیارم. هم خودت راحت کن هم منو.
آتیش خلاص شد تموم شد.
نه
این آب.
نمیخوای؟ همین الان یادت رفت. Okay. Our goal in writing this book was to provide a clear and simple account of the key ideas and algorithms of reinforcement learning. We wanted our treatment to be accessible to readers in all of the related disciplines, but we could not cover all of this perspective in detail. For the most part, our treatment takes the point of view of artificial intelligence and engineering. In this second edition, we plan to have one chapter summarizing the connections to psychology and neuroscience, which are many and rapidly developing. Converge of connections to other fields will leave to others or to another time. We also choose not to produce a rigorous formal treatment of reinforcement learning. We did not reach for the highest possible level of mathematical abstraction and did not rely on a theorem proof format. We tried to choose a level of mathematical detail that points the mathematically inclined in the right direction without distracting from the simplicity and potential generality of the underlying ideas. The book consists of 3 parts. Part 1 is introductory and problem-oriented. We focus on the simple aspects of reinforcement learning and on its main distinguishing features. One full chapter is devoted to introducing the reinforcement learning problem, whose solution we explore in the rest of the book. Part 2 presents tabular versions, assuming a small finite state space, of all the basic solution methods based on estimating action values. We introduce dynamic programming, Monte Carlo methods, and temporal difference learning. There is a chapter on eligibility traces which unifies the latter 2 methods, and a chapter that unifies planning methods, such as dynamic programming and a state space search, and learning methods such as Monte Carlo and temporal difference learning. Part 3 is concerned with extending the tabular methods to include various forms of approximation, including function approximation, policy gradient methods, and methods designed for solving of policy learning problems. Part 4 surveys some of the frontiers of reinforcement learning in biology and applications. Alright, so 3 parts. Part 2 presents the algorithms, Part 1 represents the problems, and Part 3 extends the tabular methods to include various forms of the approximation methods, policy gradient methods, and methods designed for solving of policy problems. I can write some of these. Um, well, there's not much to write right now, but this book was designed to be used as a text in a 1 or 2 semester course, perhaps supplemented by readings from the literature or by more mathematical texts such as Bertsekas and Tisiculus or Shidze Peswari 2010. This book can be used as part of a broader course on machine learning, artificial intelligence, or neural networks. In this case, it may be desirable to cover only a subset of the material. We recommend covering Chapter 1 for a brief overview, Chapter 2 through Section 2.2, Chapter 3 except Section 3.4, 3.5, and 3.9, and a selection section for the remaining chapters according to time and interest. The 5 chapters... Okay, so what chapters was it? Maybe desirable... Okay. The 5 chapters of Part 2 build on each other and are best conveyed in sequence of these. Chapter 6 is the most important for the subject, and for the rest of the book, Okay, so there are a lot of thank yous here. We can skip that. Summary of notations. Capital letters are used for random variables and major algorithm variables. Lowercase letters are used for the values of random variables. Capital letters are used for random variables, and major lowercase letters are used for the values of random variables. This may be good to probably just print out. Quantities that are required to be real valued vectors are written in bold and in lowercase. Lowercase letters are used for the values of random and for scalar. Okay, so state is S, action is A, set of all non-terminal states is S, set of all states including the terminal is S plus, set of actions possible in a state S is A of S, R is a set of possible rewards. Alright, rewards, terminal state, T is discrete time step, T capital is final time step of an episode, state at T, action at T, RT, reward at T, depending on that's an interesting point. The time of it matters too, probably. Cumulative discounted reward is GT, and a step return is that G gamma T is gamma return. Pi is policy decision making rule. Pi is action taken in state as under deterministic policy pi. Probability of taking action A in a state as under stochastic policy. And P S prime R is the reward. S is the action. A probability of transition into state S prime with reward R from SA. Interesting. Value of state S under policy pi. Value of state S under the optimal policy. Value of taking action A in a state S under policy pi. Value of taking action A in a state S under the optimal policy. Estimate a random variable of value of policy pi S or the. Estimate a random variable of, and there's pi value of optimal policy. Oh wow. On the optimal policy, so you can have not optimal policy, you can just have a pi. Action taken, probability of action taken. Okay. V vector, approximate value of a state as given a vector of weights W, Q hat, approximate value of a state action pair SA given weights W, vector of possible learned weights underlying an approximate value function, vector of features visible when in state S, inner product of vector W transpose X, there's that, vector of features visible when in state S, vector of possibly learned weights underlying an approximate value function, temporal difference error at T, a random variable even though not our case, eligibility trace for state S, eligibility trace, that's a new word. Discount rate parameter. Discount rate parameter, probability of random action in epsilon greedy and tempo at R. It is probably the number of steps that you can think of, because it says discrete time step, so kind of makes sense. Estimate a random variable of value of policy, optimal policy Q was value of taking action, value of state. Ooh. Value of state, value of taking. Value we need to some value to the state the value to change state. Alright. Alright. Um, Good enough, maybe. Temporal random even though not uppercase. Um, so the capital ones were reward at T. Pendants like ST on state at T. Okay. Probably need to see these being used. Vector of possible learned weights underlying an approximate value function. Vector of features visible when in a state S. Inner product of vectors. Temporal difference error rate at T. There's all of that. Alright. Okay. The reinforcement learning problem. The idea that we learn by interacting with our environment is probably the first to occur to us when we think about the nature of learning. When an infant plays, waves its arms, or looks about, it has no explicit teacher, but it does have a direct sensory-motor connection to its environment. Exercising this connection produces a wealth of information about cause and effect, about the consequences of actions, and about what to do in order to achieve goals. Throughout our lives, such interactions are undoubtedly a major source of knowledge about our environment and ourselves. Whether we are learning to drive a car or to hold a conversation, we are accurately aware of how our environment responds to what we do, and we seek to influence what happens through our behavior. Learning from interaction is a foundational idea underlying nearly all theories of learning and intelligence. In this book, we explore a computational approach to learning from interaction. Rather than directly theorizing about how people or animals learn, we explore idealized learning situations and evaluate the effectiveness of various learning methods. That is, we adopt the perspective of an artificial intelligence researcher or engineer. We explore designs for machines that are effective in solving learning problems of scientific or economic interest, evaluating the designs through mathematical analysis or computational experiments. The approach we explore, called reinforcement learning, is much more focused on goal-directed learning from interaction than our other approaches to machine learning. Mountaineering, is that simultaneous? Okay. Should we read these? Covering structure in an agent's experience can certainly be useful in reinforcement learning, but by itself does not address the reinforcement learning agent's problem of maximizing a reward signal. We therefore consider reinforcement learning to be a third machine learning paradigm, alongside of supervised learning and unsupervised learning, and perhaps other paradigms as well. Yeah, let's read it. The terms supervised learning and unsupervised learning appear to exhaustively classify machine learning paradigms, but they do not. Although one might be tempted to think of reinforcement learning as a kind of unsupervised learning because it does not rely on examples of correct behavior, reinforcement learning is trying to maximize a reward signal instead of trying to find hidden structure. Uncovering structure in an agent's experience can certainly be useful in reinforcement learning, but by itself does not address the reinforcement learning agent's problem of maximizing a reward signal. We therefore consider reinforcement learning to be a third machine learning paradigm. Alongside that, alongside supervised and unsupervised. One of the challenges that arise in reinforcement learning and not in other kinds of learning is the trade-off between exploration and exploitation. To obtain a lot of reward, a reinforcement learning agent must prefer actions but it has tried in that prefer actions that it has tried in the past and found to be effective in producing reward. But to discover such action, it has to try actions that it has not selected before. The agent has to exploit what it already knows in order to obtain reward, but it also has to explore in order to make better action selections in the future. The dilemma is that neither exploration nor exploitation can be pursued exclusively without failing at the task. The agent must try a variety of actions and progressively favor those that appear to be best. On a stochastic task, each action must be tried many times to gain a reliable estimate its expected reward. The exploration and exploitation dilemma has been intensively studied by mathematicians for many decades. In chapter 2. For now, we simply note that the entire issue of balancing exploration and exploitation does not even rise in supervised and unsupervised learning, at least in their purest forms. Another key feature of reinforcement learning is that it explicitly considers the whole problem of a goal-directed agent interacting with an uncertain environment. Considers the whole problem of a goal-directed agent interacting with an uncertain environment. This is the contrast with many approaches that consider sub-problems without addressing how they might fit into a larger problem. For example, we have mentioned that much of learning research is concerned with supervised learning without explicitly specifying how such an ability would finally be useful. Other researchers have developed theories of planning with general goals, but without considering planning's role in real-time decision-making or the question of where the predictive models necessary for planning would come from. Although these approaches have yielded many useful results, their focus on isolated subproblems is a significant limitation. Reinforcement learning takes the opposite tack, starting with a complete interactive goal-seeking agent. All reinforcement learning agents have explicit goals, can sense aspects of their environment, and can choose action to influence their environments. Moreover, it is usually assumed from the beginning that the agent has to operate despite significant uncertainty about the environment it faces. When reinforcement learning involves planning, it has to address the interplay between planning and real-time action selection, as well as the question of planning. For learning research to make progress, important subproblems have to be isolated and studied, but they should be subproblems that play clear roles in complete interactive goal-seeking agents, even if all the details of the complete agent cannot yet be filled in. One of the most exciting aspects of modern reinforcement learning is its substantive and fruitful interactions with other engineering and scientific disciplines. Reinforcement learning is part of a decades-long trend within artificial intelligence and machine learning toward greater integration with statistics, optimization, and other mathematical subjects. For example, the ability of some reinforcement learning methods to learn with parameterized approximators address the classical case of dimensionality in operations, research, and control theory. Parameterized approximator's address. Where were we? Here's a dimensionality. Parameterized approximators. There's classical currency operations research and control theory. Alright. More distinctively, reinforcement learning has also interacted strongly with psychology and neuroscience, with substantial benefits going both ways. Of all the forms of machine learning, reinforcement learning is the closest to the kind of learning that humans and other animals do, and many of the core algorithms of reinforcement learning were originally inspired by biological learning systems. And reinforcement learning has also given back both through a psychological model of animal learning that better matches some of the empirical data and through an influential model of parts of the brain's reward system. The body of this book develops the ideas of reinforcement learning that pertain to engineering and artificial intelligence, with connections to psychology and neuroscience summarized in chapters. There were 2 sections for it. I don't remember. I don't understand why they did this either. Finally, reinforcement learning is also part of a larger trend in artificial intelligence back toward simple general principles. Since the late 1960s, many artificial intelligence researchers presume that there are no general principles to be discovered. The artificial intelligence is instead due to the possession of vast numbers of special purpose tricks, procedures, and heuristics. It was sometimes said that if we could just get enough relevant factors into a machine, say 1 million or 1 billion, then it would become intelligent. Methods based on general principles such as search or learning were characterized as weak methods, whereas those based on specific knowledge were called strong methods. This view is still common today, but much less dominant. From our point of view, it was simply premature. Too little effort had been put into the research for general principles to conclude that there were none. Modern AI now includes much research looking for general principles of learning, research, and decision making, as well as trying to incorporate vast amounts of domain knowledge. It is not clear how far back the pendulum will swing, but reinforcement learning research is certainly part of the swing back towards simpler and fewer general principles of artificial intelligence. Or Alright, examples. A good way to understand reinforcement learning is to consider some of the examples and possible applications that have guided its development. A master chess player makes a move. The choice is informed both by planning, anticipating possible replies, and counter replies. and by immediate intuitive judgments of the desirability of particular positions and movement and moves. An adaptive controller adjusts parameters of a petroleum refinery's operation in real time. Okay. The control optimizes the yield cost quality trade off on the basis of specified marginal costs without sticking strictly to the set points originally suggested by engineers. A gazelle calf struggles to its feet minutes after being born. Half an hour later, it is running at 20 miles per hour. A mobile robot decides whether it should enter a new room in search of more trash to collect or start trying to find its way back to its battery recharging station. It makes its decision based on the current charge level of its battery and how quickly and easily it has been able to find the recharger in the past. Phil prepares his breakfast, closely examined. Even this apparently mundane activity reveals a complex web of conditional behavior and interlocking goal sub-goal relationships. Walking to the cupboard, opening it, selecting a cereal box, then reaching for, grasping and retrieving the box. Other complex tuned interactive sequences of behavior are required to obtain a bowl, spoon, and milk jug. Each step involves a series of eye movements to obtain information and to guide reaching and locomotion. Rapid judgments are continually made about how to carry the objects or whether it is better to ferry some of them to the dining table before obtaining others. Each step is guided by goals such as grasping a spoon or getting to the refrigerator as in service of other goals, such as having the spoon to eat with once the cereal is prepared and ultimately obtaining nourishment. Whether he's aware of it or not, Phil is accessing information about the state of his body that determines his natural nutritional needs, level of hunger, and food preferences. Those examples share features that are so basic that are easy to overlook. All involve interaction between an active decision-making agent and its environment, within which the agent seeks to achieve a goal despite uncertainty about its environment. The agent's actions are permitted to affect the future state of the environment. The next chess position, the level of reservoir of the refinery, the robot's next location, and the future charge level of its battery, thereby affecting the options and opportunities available to the agent at later times. Correct choice requires taking into account indirect delayed consequences of actions and thus may require foresight or planning. At the same time, in all these examples, the effects of actions cannot be fully predicted. Thus, the agent must monitor its environment frequently and react appropriately. For example, Phil must watch the milk he pours into the cereal bowl to keep it from overflowing. All those examples involve goals that are explicit in the sense that the agent can judge progress toward its goal based on what it can sense directly. The chess player knows whether or not he wins. The refinery controller knows how much petroleum is being produced. The mobile robot knows when its batteries run down. And Phil knows whether or not he's enjoying his breakfast. Neither the agent nor its environment may coincide with what we normally think of as an agent and its environment. An agent is not necessarily an entire robot or organism, and its environment is not necessarily what is outside of a robot or organism. The example robot's battery is part of the environment of its controlling agent, and Phil's degree of hunger and food preferences are features of the environment of his internal decision-making agent. The state of an agent's environment often includes information about the state of the machine or organism in which the agent resides. And this can include memories, even aspirations. Throughout this book, we are being abstract in this way when we talk about agents and their environment. In all of these examples, the agent can use its experience to improve its performance over time. The chess player refines the intuition he uses to evaluate positions, thereby improving his play. The gazelle calf improves the efficiency with which it can run. Phil learns to streamline making his breakfast. The knowledge the agent brings to the task at the start, either from previous experience with related tasks or built into by design or evolution, influences what is useful or easy to learn, but interaction with the environment is essential for adjusting behavior to exploit specific features of the task. Elements of reinforcement learning. Okay. Go to tic-tac-toe. And then we go to history of that. Right, perfect. It was 1.2, wasn't it? Examples 1.3. Beyond the agent and the environment, one can identify four main sub-elements of a research reinforcement learning system. A policy, a reward signal, a value function, an option, a model of the environment. A policy defines the learning agent's way of behaving at a given time. Roughly speaking, a policy is a mapping from perceived states of the environment to actions to be taken when those states. It corresponds to what in psychology we would call a set of stimulus-response rules or associations, provided that stimuli include those that can come from within the animal. In some cases, the policy may be simple function or lookup table, whereas in others, it may involve extensive computation such as a search process. The policy is the core of a reinforcement learning agent. Oh, let me add something here. The changing of rewards. Changing of rewards by time as time goes by. So then we are in the middle. Yeah, this is probably another 6 months of work. This is very likely another 6 months of work. Yeah, I mean, what can you do? It's pretty fun. So maybe you're in the middle of the game. So let's change that to, for example. Maybe be more hidden or way ahead. Yes. Yes. Okay. In some cases, the policy may be a simple function or lookup table, whereas in others it may involve extensive computation such as a research process. The policy is the core of a reinforcement learning agent in the sense that it is alone to sufficient that it alone is sufficient to determine behavior. In general, policies may be stochastic. Um, the reward signal defines the goal in a reinforcement learning problem. On each time step, the environment sends to the reinforcement learning agent a single number, a reward. The agent's sole objective is to maximize the total reward it receives over the long run. The reward signal thus defines what are the good and bad events for the agent. In a biological system, we might think of rewards as analogous to the experiences of pleasure or pain. They are the immediate and defining features of the problem faced by the agent. The reward sent to the agent at any time depends on the agent's current action and the current state of the agent's environment. The agent cannot alter the process that does this. The only way the agent can influence the reward signal is through its actions, which can have a direct effect on reward or an indirect effect through changing the environment's state. In our example above of Phil eating breakfast, the reinforcement learning agent directing his behavior might receive different reward signals when he eats his breakfast depending on how hungry he is, what mood he is in, and other features of his body, which is part of his internal reinforcement learning agent's environment. The reward signal is the primary basis for altering the policy. If an action selected by the policy is followed by low reward, then the policy may be changed to select some other action in that situation in the future. In general, reward signals may be stochastic functions of the state of the environment and the actions taken, whereas the reward signal indicates what is good in an immediate sense. A value function specifies what is good in the long run. Roughly speaking, the value of a set is the total amount of reward an agent can expect to accumulate over the future, starting from that state, whereas rewards determine the immediate intrinsic desirability of environmental states. Values indicate the long-term desirability of states after taking into account the states that are likely to follow and the rewards available in those states. For example, a state might always yield a low immediate reward but still have a high value because it is regularly followed by other states that yield high rewards. Or the reverse could be true. To make a human analogy, rewards are somewhat like pleasure if high and pain if low. Like pleasure if high and pain if low. Whereas values correspond to a more refined and far-sighted judgment of how pleased or displeased we are at that our environment is in a particular state. Expressed this way, we hope it is clear that value functions formalize a basic and familiar idea. Um, so for example, for a game, is the value the winning of that game? Right. Let's move on. Rewards are in a sense primary, whereas values as predictions of rewards are secondary. Without rewards, there could be no values, but the only purpose of estimating values is to achieve more rewards. Okay, nevertheless, it is values with which we are most concerned with when making and evaluating decisions. Actions, choices are made based on value judgments. We see actions that bring about states of highest value, not highest reward, because these actions obtain the greatest amount of reward for us over the long run. In decision making and planning, the derived quantity called value is the one with which we are most concerned. Unfortunately, it is much harder to determine values than it is to determine rewards. Rewards are basically given directly by the environment, but values estimate must be estimated and re-estimated from the sequences of observations an agent makes over its entire lifetime. In fact, the most important component of almost all reinforcement learning algorithms we consider is a method for efficiently estimating values. The central role of value estimation is arguably the most important thing we have learned about reinforcement learning over the last few decades. The fourth and final element of some reinforcement learning system is a model of the environment. This is something that mimics the behavior of the environment, or more generally, that allows inferences to be made about how the environment will behave. For example, given a state and action, the model might predict the resultant next state and next reward. Models are used for planning, by which we mean any way of deciding on a course of action by considering possible future situation before they are actually experienced. Methods for solving reinforcement learning problems that use models and planning are called model-based methods. As opposed to simpler model-free methods that are implicitly trial and error learners. Alright. Model-free methods that are explicit trial and error learners viewed as almost the opposite of planning. Chapter 9, we explore reinforcement learning systems that simultaneously learn by trial and error, learn a model of the environment, and use the model for planning. Modern reinforcement learning spans the spectrum from low-level trial and error learning to high-level deliberative planning. Sure. Model is planning. Trial and error is supposedly the opposite of it. Limitations in the scope. Let's see how much. It's already 2 hours. Okay. Gonna finish with 10 pages. I thought we could get to 50 pages, but apparently no. Most of the reinforcement learning methods we consider in this book are structured around estimating value functions, but it is not strictly necessary to do this to solve reinforcement learning problems. For example, methods such as genetic algorithms, genetic programming, simulated annealing, and other optimization methods have been used to approach reinforcement learning problems without ever appealing to value functions. These methods evaluate the lifetime behavior of many non-learning agents, so each using a different policy for interacting with its environment, and select those that are able to obtain the most reward. We call these evolutionary methods because their operation is analogous to the way biological evolution produces organisms with a skilled behavior even when they do not learn during their individual lifetimes. If the space of policy is sufficiently small or can be structured so that good policies are common or easy to find, or if a lot of time is available for or the search, then evolutionary methods can be effective. In addition, evolutionary methods have advantages on problems in which the learning agent cannot accurately sense the state of its environment. Our focus is on reinforcement learning methods that involve learning while interacting with the environment, which evolutionary methods do not do unless they evolve learning algorithms. Evolutionary methods do not do that. Unless they evolve learning algorithms in some of the approaches that have been studied, it is our behavior that methods able to take advantage of the details of individual behavioral interactions can be much more efficient than evolutionary methods in many cases. Evolutionary methods ignore much of the useful structure of the reinforcement learning problem. They do not use the fact that the policy they are searching for is a function from states to actions. They do not notice which states an individual passes through during its lifetime, or which actions it selects. In some cases, this information can be misleading when states are misperceived, but more often it should enable more efficient search. Although evolution and learning share many features and naturally work together, we do not consider evolutionary methods by themselves to be especially well suited well suited to reinforcement learning problems. For simplicity, in this book, when we use the term reinforcement learning method, we do not include evolutionary methods. However, we do include some methods that, like evolutionary methods, do not appeal to value functions. These methods search in the spaces of policies defined by a collection of numerical parameters. They estimate the directions, the parameters should be adjusted in order to most rapidly improve a policy's performance. Unlike evolutionary methods, however, they produce these estimates while the agent is interacting with its environment, so can take advantage of the details of individual behavior interactions. Methods like these, called policy gradient methods, have proven useful in many problems, and some of the simplest reinforcement learning methods fall into this category. In fact, some of these methods take advantage of value functions estimates to improve their gradient estimates. Overall, the distinction between policy gradient methods and other methods we include as reinforcement learning methods is not sharply defined. Reinforcement learning's connection to optimization methods deserves some additional comment because it is a source of a common misunderstanding. When we say that a reinforcement learning agent's goal is to maximize a numerical reward signal, we of course are not insisting that the agent has to actually achieve the goal of maximum reward. Trying to maximize a quantity does not mean that quantity is ever maximized. The point is that a reinforcement learning agent is always trying to increase the amount of reward it achieves. Many factors can prevent it from achieving the maximum, even if one exists. In other words, optimization is not the same as optimality. To illustrate the general idea of the reinforcement learning and contrast it with other approaches, we next consider a simple sample in more details. Consider the familiar child's game of tic-tac-toe. Two players take turns playing on a 3x3 board. One player plays X and the other one plays O and other O's until one player wins by placing 3 marks in a row, horizontally, vertically, or diagonally, as the X player has in this game. If the board fills up with neither player getting 3 in a row, the game is a draw because the skilled player can play so as never to lose. Let us assume that we are playing against an imperfect player, one whose play is sometimes incorrect and allows us to win. For the moment, in fact, let us consider draws and losses to be equally bad for us. How might we construct a player that will find the imperfections in its opponent's play and learn to maximize its chances of winning? Alright, that's it for this video. Well, we learned the 4 important things: the policy, the reward, the value function, and let's just go over it one more time. Value function. It's a model, the planning part. So you need to plan. All of these is to maximize your rewards. All of this is to maximize your rewards, and because of that, the whole thing should work. Okay, we learned a little bit of these notations. We also went over the backgammon. We said, so big problem, like you said, in reinforcement learning is about designing that value function. And that value function is actually what's really important. There's that. We added some stuff to the backgammon. We added some stuff to the backgammon. So the changing of rewards is just the time, the value function according to time. How do you write the value function? Excuse me. We went through that. Maybe we should have skipped those examples. What I'm thinking is like does policy change? Like if you have robotic soccer players or some robotic, like should we make it to learn things like that or no? What else? Yeah, just took a look at that and probably have number of actions for in the future looking. Maybe is it always better to look more It is probably to look more. If we are not limited, probably. Okay. Yeah. I'm gonna cut this short, hour and 50 minutes. But I will come back to this tomorrow, definitely. Thank you for watching, and hopefully we're gonna finish the backgammon.